In this next module, we will be talking about Gauss's law. Gauss's law concerns the flux of the electric field. And as you know, we talked previously about the fact that if we have a positive charge, we found that it emits an electric field outward in every direction. We could think of this vector field, E, which goes outward away from this charge, as a vector field which is flowing almost like a velocity, where we have a movement away from the positive charge. If we have a negative charge, the electric field moves inward towards this charge. It's not an actual motion, but it's a direction, and it's the same sense of a vector. And what we can talk about, as with any vector field which represents a type of flow, we can talk about the flux of a vector field through a surface. Let's imagine that we have an electric field that looks like this, or any vector field. And we could imagine a surface that had a certain area A, and we could define a concept of flux. Flux is normally represented by the symbol phi, and you can see that equation right here. And flux is defined as the vector field, in this case E, or in this case up here V, for any vector field, and its dot product with an area A. Well, the first thing that you'll say is, how does the area A become a vector? And the answer is, we can consider an area A as a vector. We'll imagine a vector that points on the far side of this, that's perpendicular to the surface and has a length that's associated, that's exactly equal to its area. So the length of this vector is its area, and the direction points perpendicular to its surface. And so now you can see that the electric field dotted with the field A, or if we wish here, the area A is pointing in this direction here, and so E dot A is going to be the same as E times A times the cosine of the angle between them. But the angle between E and A is 0. Therefore the cosine is 1, and all of this flux goes through this area. And so it's simply the product of the electric field times the amount of area that you have. So if you had an electric field which is equal to 6, now what is that 6? You recall that the electric field is the force per unit charge. So this would be newtons per coulomb. So if we have an E that's 6 newtons per coulomb, and we had an area that's 4 square meters, then the flux phi that would be defined by this would be 6 times 4, which is 24 Newton meters squared per coulomb. And that would define our flux that went through this surface. Now if this surface were tilted at an angle, or the electric field is at an angle, of course not as much goes through it. One example of something like this is sunlight. When sunlight falls on something, if it falls at an angle like it does on the ground in the winter, it's much less effective in its warming. And so there's not as much solar flux through a given area on the ground. In that same sense, if the electric field were to go in another direction, and let's imagine again our area A, but now we're going to take the flux of the electric field as pointing in this direction here and coming through the surface. And the perpendicular to the surface would be the area A here. And here's the electric field. You can see that there's an angle theta between the two. And the only thing that's effective for determining the flux is then that part of the electric field that projects in the direction of A, and that of course is E cosine theta, which is exactly what we have in our equation. And so if the two are at an angle, we must remember to use the cosine of the angle between them in order to compute the flux. Gauss's law makes a very definite statement about the flux of an electric field through a closed surface. It says two things. First of all, if I have an electric field, here's an electric field, and I have any kind of surface whatsoever, then if the electric field issues from outside of this surface, S, then the total flux through this surface is equal to 0. Now, why would that be? Well, this electric field is originating from charges Q, which are outside the surface. And you'll notice that the electric field must enter the surface in one place and exit the surface in another place. So every line that goes in over here must go out over here because it didn't originate inside and it goes to infinity. Therefore, it follows that the flux is equal to 0 from any charge on the outside. In the second instance, what we have is we have a charge that's inside. If we think about a charge being inside that same surface, here's a charge Q, then the electric field goes out in every direction. And you can see from this that the electric field through the surface, and the surface is always taken as little segments of surface area which point outward from any closed surface, and that defines which way it's going. So we have an area pointing outward, an electric field here, and if we add those up, you can say, well, what would we get? Well, we obviously get something because all of this flux is going out through the surface. That looks like a hard problem. It is rather difficult, but there's a simple way to look at it. If we imagine we have a sphere and we put a charge in the direct center of that sphere, then the electric field will come out in each direction, and as it comes out, it will go through an area at the same distance away from the surface. Now, what is this electric field here? Well, the electric field at this point, remember this is just an imaginary surface here, the electric field is going to be the charge Q times K divided by R squared. KQ over R squared, where this is the distance R out to this point. Well, that gives us the electric field at this point, as we found in the last module. Well, what is this area? Well, this is a little tiny area here, but you'll notice that the electric field goes in the same direction as the area for a sphere. So they're pointing in the same direction, the electric field here, the area here. And if we add those up all the way around, we can see that the area points out, the electric field points out, so there's no cosine of theta that we have to worry about. So we just have to take E everywhere times the area everywhere. Well, E is constant over this entire surface of a sphere because the charge is located exactly in the center. So what we have to do is we have to integrate or add up all the infinitesimal pieces of surface, d sigma, as they occur here. Now, if you are not familiar with your calculus, what we're doing is we're just saying add up all the small areas on a sphere. Well, what is that? That is that's the total surface of a sphere. That's the area of a sphere. And of course, this formula here then becomes E is equal to KQ divided by R squared, and this is 4 pi R squared, the area of a sphere. And so now you see from this is the total flux now. It's E times the area, E times the area, and our R squared cancels our R squared, and so what we get is KQ times 4 pi. But you recall that K is 1 over 4 pi epsilon naught. I'll put the charge up here on top, times 4 pi. And in this form, the 4 pi cancels the 4 pi, and we can see that the flux through a sphere is equal to Q that's inside divided by epsilon naught, which is permittivity of free space. Well, that's exactly what this equation is right here. The flux through a closed surface is the charge inside over epsilon naught. We proved it here for a sphere, but in fact it applies to any surface. So if I take a charge and put any kind of surface around it, and it's on the inside, then the total flux through that is Q inside over epsilon naught. Now, a common problem that I'll give you on a test is I'll put some various charges here. I'll put 2 coulombs here, minus 3 coulombs here, 4 coulombs here, minus 1 coulombs here, 2 coulombs here, and I'll say, what is the flux through the surface? Well, just remember that the charges that are outside don't count at all because their flux goes in one place and out the other. You add up algebraically, meaning keeping the signs, all those that are on the inside. So that would be 4 coulombs, 5, 6, minus 1. So it's 5 coulombs. So the answer is the flux is equal to 5 coulombs divided by epsilon naught. 5 over epsilon naught. And if you had to have a numerical value here, you can always multiply by 4 pi and divide by 4 pi, and 1 over 4 pi epsilon naught is K electric, and that would be K electric times 20 times pi. And of course, as you know, this is 9 times 10 to the 9th, and you're required to know that. A more formal definition in vector calculus is given, as we said right here, where we integrate that over the whole surface. And you do get, for those of you who are familiar with calculus, this very difficult integral over this whole surface, and that's the representation of it. Well, Gauss's law can be used to compute the electric field in cases that are symmetric. And the electric field is 0 anywhere inside a conductor. Thus, conductors can be used to shield the inside region from an outside electric field. So if we take a conductor, and I have a conductor here, now this is not an imaginary surface, but a conducting surface, like it's a sheet of copper. Then any electric field that we have outside is shielded, and the charge will build up here to compensate for that electric field. And so inside, the electric field is equal to 0 anywhere anytime that we're inside a conductor. All the excess charge that's on a conductor, even if we put charge on it, it will accumulate on the surface. Even if we put charge down in here, if it can flow, this is a solid conductor, it will flow immediately to the surface, repelling other like charges, and go to the surface and get as far away from the rest of it as it possibly can. And I just did a simple flux calculation for several charges inside a closed surface, and that's what you're required to do for the test. You should understand what flux is. You should understand the dot product of any vector field with the area. In our case, it's the electric field. And of course, this is Gauss's law. And we're going to apply in the next few modules this Gauss's law to different symmetric cases and find a useful way to take Gauss's law and determine the electric field.